Welcome to Chemistry 112. So today we're going to continue on talking about our electrochemistry. We're going to try to relate this to like equilibrium constant K, relate it to Gibbs free energy. We're going to talk about electroplating and like electrolytic cells, and talk about some interesting related chemistry, like some direct applications of electrochemistry. This is the last major chapter with a major homework assignment. We will go into the next chapter, which is nuclear chemistry. There will be some reading, there will be some learning curve, but there is not an assessment for the nuclear chemistry chapter. However, there may be 1 or 2 questions on the test from nuclear chemistry chapter. But the main homework you'll need to be able to do there, some of it's just kinetics again, so you may need to just refresh your kinetics. But until we get done with those, we have a little bit of time before test 4. In the meantime, just keep working on it. Don't forget, you need to do at least 3 online labs. If you have missed 2 or more labs, you probably should come and make them up, set up a time, come get some help. Make sure to be turning in your lab things so I can get grades and get them into the grade book. Pretty much if you did not get a satisfactory grade in lab, it could be just due to not having all your grades turned in. So as soon as that happens, it should change. Last class period, last Thursday, we talked about how to calculate E cell potential. We would look at a chemical reaction, look at which reactant was reduced, which reactant was oxidized, and then find those relative chemical reactions on the reduction potential table. Notice it is the reduction potential table. All of the values on the reduction potential table are given as reductions. So one of the reactions will match the half reaction exactly. One of the reactions will be the reverse of your chemical reaction. And basically, you will take those 2 numbers, those 2 E cells, and subtract the oxidation from the reduction. So you will take the one that appears identically and subtract the one that appears inverse from the other. And that's how we calculated the E cell. You did not have to take into account the moles. You didn't have to balance anything because the E cell takes into account the number of electrons. It's the voltage per electron. And so when we do it all together, it works its way out perfectly. Now, we're going to relate that E cell, that cell potential, to the Gibbs free energy. That the cell potential has to do with the spontaneity of the reaction. And so our main equation here is that delta G is equal to negative N F E. Now this N and F are 2 really kind of newish things we have not seen. Now N used to be the moles of reaction, that we might have used it in, say, the ideal gas equation, PV equals nRT. But this N is a little bit different because what we're trying to get is turn volts into joules or even kilojoules. So we need both Faraday's constant, which is something that'll always be given, but it's a constant that you could memorize if you so needed to, and moles of electrons. So in this case, we're considering how many electrons are being transferred. Now, Faraday's constant is 96485, and that's units of coulombs per moles of electrons. However, a coulomb volt is equal to a joule. A coulomb volt is equal to a joule. So we can exchange that coulomb into a joule per volt. So if I take a joule per volt per mole of electron and multiply it by a cell potential, which is in volts, we would get joules per mole of electron. Now the N will then convert that moles of electron into like moles of reaction. And so by taking negative NFE, we will get joules per reaction. And of course, once again, watching out for your units. Watching out for your units, you should get kilojoules per reaction. Typically, when they ask you to present a delta G value, they want it in kilojoules. Now, where does the number for Faraday's constant come from? It's just a rearrangement of two numbers we hopefully know, but one of them we don't know very well. Number one is the charge of an electron. Briefly discussed way back in chapter 2 when we talked about the subatomic components of an atom. Someone had managed to discover, well, the charge of an electron is equal to 1.602 times 10 to the negative 19th coulombs. That was, I'd like to say that was maybe Thomas Millikan. And well, because we're not dealing with singular electrons, but dealing with moles of electrons, then we have to turn singular electrons into moles by using Avogadro's number. So if you take the charge of an electron, multiply it by Avogadro's number, you get 96485, or coulombs per mole of electron. But once again, much like Boltzmann distribution, we don't need to the Boltzmann's constant. We don't need to necessarily know where it comes from. It's just a neat little fact. So if I was to calculate this simple reaction, nickel plus 2 silver solution goes to nickel solution and 2 silver solid. We see a 2 electron transfer. And if we were to calculate the cell potential for this, it would be 1.08 volts. So what would I do? I'd take 1.08 volts times 96485 times 2, because there's nickel lost 2, silver gained 2 electrons, and make it negative. Now that would give you a really big number. However, once you divide by 1,000, it becomes still a rather large number. Negative 208.4 kilojoules per reaction. Now, a lot of the Gibbs free energy that we've been dealing with, we've been talking about like maybe 50, maybe 100. So to have something that's on the scale of negative 208 kilojoules, negative 208 kilojoules is very large indeed. Very large indeed. Now, which makes this very spontaneous. If I put silver solution, nickel solid into silver solution, it will rapidly begin to react and create a large voltage. Now, because E relates to G and G relates to K, we can relate E to K. So remember, we said delta G equals negative NFE. And last chapter, we said delta G equals negative RT ln K. And so we can exchange the equations and isolate the E. So what we do is when we divide both sides by negative NF, we get E equals RT over NF ln K. R is in 8.314. T is our temperature in Kelvin. N is our moles of electrons. And F is our Faraday's constant. This is one time we don't have to watch out for units because this converts volts into joules, and then R cancels out joules. And that equals the natural log of our K. So remember, a large positive E cell will mean a very spontaneous reaction. A large positive E cell would mean a K that is rather large, which means rather product favored. If I do that same reaction, 1.08 volts, so times 2 times 96485 divided by 8.314 divided by 298. If I do that all by itself without doing the natural log, do that without doing the natural log. Let's see. What's the number? I left my calculator. Before I do the natural log, that is, let's see, times 2 times 96485 divided by 8.314 divided by 298. So this, we're saying 84.11 equals natural log of K. So remember, we have to take the inverse log to both sides. And so the products are, the K is going to be 3.39 times 10 to the 36th. Our K expression would be nickel 2 plus over silver plus squared, because we wouldn't include the solids. But the idea here is that the ratio of silver to nickel is essentially broken. Very much so. You'd have an incredibly small number of silver left in solution and a very large amount of nickel in solution. Now, so let's look at this. Simple reaction. Sodium plus chlorine goes to 2 sodium chloride. What would happen to this? We have sodium, right, this 2 sodium solid plus chlorine gas goes to 2 sodium chloride, aqueous. Well, we're going to break this down to 1/2 reaction is Na plus electrons, Na, and that's negative 2.71. Chlorine, 2 electrons, goes to 2 chloride, and that's 1.359. So I'm at 25 degrees, which is 298 Kelvin. What is our G? What is our K? Go into the doc cam. First thing we need to do is calculate our E. In this reaction, this guy is being reduced. This guys are oxidized. This guy appears identical as up here. This guy is inverse because as they're solid, the solid is on the wrong side. So our E cell is just going to be 1.359, which is the reduction, minus negative 2.71, which is our oxidation. You do that math, you get what, like 4.069 volts. Now, our delta G value is equal to negative NFE. So it's going to be equal to negative, how many electrons get transferred? 1 per reaction, but this is whole, doubled, and 2 here. So the Number of electrons is 2. The greatest common factor between 1 and 2 is 2. Times 96485 times 4.069. All that needs to be divided by 1,000 to get this into kilojoules. 2 times 965 times 4.069 divided by 1,000. You would get, holy cow, that would be negative 785 kilojoules. So what can we say about this? Very spontaneous. You've heard of people throwing blocks of sodium in water to explode and kill fish, and way of lazy man's fishing tool. Well, let's just say chlorine is way more reactive than our water in this case. Way more reactive. And so throwing a block of sodium in water, a block of sodium and chlorine is a whole nother scenario. This is going to be highly exothermic, highly explosive. Now our K expression would actually be looking at Cl2 over Na plus squared Cl minus squared. But we don't actually need to find our K. We're going to say, what is our K? We don't need to find the individual components. We can just find our K, if we can even do that. So ln K, let's rewrite it. Ln K is going to be our E cell times NF over RT. So 4.069 times 2 times 96485 all over 8.314 and 298. So 4.069 times 2 times 96485, 8.314, 298. You get 316. The 316.9 equals ln K. And if you actually try to do the inverse log of that, your calculator is going to spit out an error. Not because this is actually wrong, but this number is too big. Okay, now my phone calculator is capable of doing it. Some calculators stop at a certain amount. The K, if I do the inverse log of both, I get 4.245 times 10 to the 137th. It's off the screen. Sorry. 4.25 times 10 to the positive 137th. So just think of how big of a number that is. How big of a number? That is, when we dealt with acids and bases, we dealt with Ks that are all like 10 to the negative 12th or 13th, or really weak base might have been 15th. When we dealt with KSP, we dealt with to the negative 34th, to the negative like 15th, to the negative like 7th. We dealt with relatively small numbers. So to have a number that is at least triple, if not quadruple, some of the biggest numbers we've dealt with should tell you how absolutely spontaneous this is. This is crazy levels of spontaneous. We would have so much sodium salt and almost, this would be considered like 100% reaction. We have so little chlorine gas, it's almost a rounding error. All that just from this. So, yeah. At least my old graphing calculator, this would come up as an overflow. Wouldn't be able to do this. Now, there's a way to calculate it, but obviously my phone calculator is a little bit smarter than apparently my old graphing calculator. Now, not all of them are going to be that crazy. But based on the Gibbs reaction, based on this reaction, what would the cell potential of this? So this is a standard reaction of the oxidation of iron. Iron is going to iron solid in the presence of acid and oxygen will naturally oxidize to 2+ and eventually to 3+. But the cell potential here is the delta G is negative 632.17 kilojoules. Let's write the equation just so we can see and break this down into, because we'll need the number of electrons. Writing this down, and 2 waters. Okay. Now going to the cam. So you should be able to go from delta G back to E and from E to delta G with relatively little problem. Is that clear enough on your guys' screen? Yeah, there we go. That might be a little bit clearer. So breaking this down into its half reactions, we have 2 iron goes to 2 iron 2+. Looking at that, how many electrons? 2 times 2, so we'd have 4 electrons lost and would have O2, and 4H plus goes to 2 waters. That's going to be 4 electrons gained. So the number of electrons total is 4. Our equation is delta G equals negative NFE. So what are we going to do? We're going to take our delta G, 632.17, times by our 1,000 because of units. This is kilojoules. We need this in joules. Divide by our negative 4 and our 96485. So calculating this, what is our cell potential for this perfectly natural reaction? We would have, okay, 4 divided by, we would have a voltage of 1.6. 0.6, we'll say 38 volts. Now we should be able to relate these two together with very little problems. Okay. Now, once again, much like in Gibbs, it's like with Gibbs, very rarely do we actually do all of our chemistry under standard state conditions. We have to be able to calculate this for non-standard conditions. And so we had a way to calculate the Gibbs non-standard, where we said delta G equals delta naught plus RTL and Q. Well, knowing that delta G equals negative NFE, we can replace delta G naught with negative NFE naught and delta G as negative NFE. Dividing both sides by negative NF, our equation becomes what's called the Nernst equation. But it's basically E non-standard equals E standard minus RT NF ln Q. Basically, we can find out the E standard just looking up on a table. But the actual voltage we get will depend on our concentrations. And so we will adjust the voltage based on this negative RT over NF ln Q. So a battery that has high concentration of products and low concentration of reactants is going to have a lower voltage. Which is why, as a battery is used, as a battery is utilized, the voltage it actually produces will go down until it eventually dies off. You'll have no voltage being produced because you'll have a large amount of products and very little reactants. But once again, and under standard conditions, Ln and thus E is at standard conditions. When it reaches equilibrium, E ln Q equals K, then this is going to be equal to this, and those are going to cancel out, and you're going to have the E cell equals 0. But basically, this equation means if we can control the concentration of our battery, we can control the voltage. We can either strengthen the voltage or weaken the voltage to get it right where we need it to be. Which brings up a weird idea of concentration cells. Now, if you read the textbook, you read online, this whole idea, this is essentially the premise of how electrical eels generate shock. They're going to have various proton channels within the body. They're going to build up a proton concentration across a gradient barrier, much like in the ATP cycle, that where we produce ATPase produces our energy in the body, that it shuttles protons to one side of the mitochondria and then they come back and we use it to make ATP. Well, the same way, by shuttling these hydrogens across the energy barrier, you create a gradation. This gradation will create a voltage. And if you release this, it can create a nasty shock that can stun predators and prey alike. Now, please note, when both of the half reactions are the same, the E standard would be 0. The E standard will be 0. If I'm going one way and then the other, and it's the same reaction, the first reaction cancels the second reaction. So the cell potential only depends on the concentration of each one. And by putting different concentrations from one cell to another, a small voltage can be generated. So in this case, this is actually wrong. It's actually a little bit wrong, but not by much. I'm going to correct this real quick. But because what is the actual half reaction that is occurring? Let's write this out. Go to .cam. So back over here. The half reaction we actually have occurring is 2H plus goes to H2, 2 electrons. And the other one is H2 goes to 2H plus and 2 electrons. So our K expression, or our Q expression, is going to be what? H2, we'll call that A, and that B, H2 over H plus squared, and H plus squared over H2. Oh, sorry. So we have this. Now, if this guy is 1, if we say the pressure is 1 atmosphere and 1 atmosphere, those ignore. But then we have to say, hey, what is the pH in cell 1 and what is the pH of cell 2? The pH of cell 1 and the pH of cell 2 were what, like 10, I can't read on my screen. Were the cell 1, where its reactance is 10 to the negative third. Cell 2 was 10 to the negative 7th. So product's 10 to the negative 7th squared over 10 to the negative third squared. So that actually changes this by a bit. This becomes Q is equal to now 10 to the negative 8th. So with this, we have E is equal to negative RT over NF ln 10 to the negative 8. So 8.314 times 298 divided by 2 divided by 96485 times ln 10 root negative 8. And oh, shoot. Okay, and basically it doubles the voltage. It would have 0.236. So it's not much of a change, but it's still we've doubled the voltage. So I've actually calculated that wrong on the slide. But 2.236 volts may not seem like much, but it can be a rather nasty shock. I mean, it's not incredibly spontaneous, but it is going to be enough to like do some damage. So, but I mean, the whole idea of the concentration cells is, in this case, by having one being a mildly good acid and the other being neutral, we can generate a rather significant voltage. It's once again much like in the G non-standard. It changes it by a couple of kilojoules here and there, maybe not a massive change, but it can still have a significant change. Enough that it would screw up your math. So looking at a problem. So as I said, sodium reacts violently with water in the following equation. That water produces hydrogen, sodium, and hydroxide. So there are 2 sodiums plus water goes to hydrogen gas, sodium hydroxide, and it produces enough heat that this usually explodes. It ignites the hydrogen that it produces. Now, if we were to dissolve enough sodium hydroxide to make a 0.25 molar solution and put this in saturated hydrogen, what would the E non-standard be? Okay, so looking at this, you would, our equation, let's rewrite it. 2Na solid plus 2H2O liquid goes to H2 plus 2Na plus and 2OH minus. I'm giving you a concentrations 0.00075 for hydrogen and 0.2 molar for sodium and hydroxide. Okay. The E cell potentials, we have negative 2.71 and negative 0.83. Step one, we have to calculate our E cell. We have to calculate our E cell. E cell is going to be negative 0.83 minus a negative 2.71. And so that becomes, no, something like 1 point, what's 1.2. Math escapes me today. 1.88 volts is our E standard. Now, our equation was E equals E standard minus RT over NF ln Q. Our Q expression would be hydrogen, sodium squared, hydroxide squared, because product raise the product coefficient. We don't include sodium solid, and we don't include water liquid. We ignore those entirely. So Q is going to be equal to, so we got to find Q. Now, these guys, these type of problems, you want to work them out systematically because there's so many moving parts. You can very easily screw things up. I would suggest you solve Q first, then write Q down, and then I can use Q later. Q is equal to 2.9297 times 10 to the 1, 2, 3, 4, 5, 10 to the negative 6th. Yeah, 10 to the negative 6, 2.2927. So we have 1.88 minus 8.314 times 298. How many electrons? 2 are lost. 2 gained. 485 ln 2.9297 E negative 6. Now, maybe you want to solve this in parts. Maybe you want to solve it all at once. It depends on how nice a calculator you have. Okay, let's do this. Okay, I'm going to say 1.88 minus 8.314 times 298 divided by 2 divided by 96485 times my natural log of the answer. By doing this, your voltage goes up to 2.04 volts. Your voltage is increased by a small amount. Not a humongous amount, but it is a jump of 1.6 volts, 0.16 volts. And God, remember, this number, this 1.88, assumes this number is 1 molar, 1 molar, 1 molar. That 1.88 assumes those are 1 molar, 1 molar, 1 molar. So by having these concentrations, the voltage has gone up. Because they're less than 1 means it is not quite to the standard state conditions. It needs to proceed to further reaction. So that's kind of a nitpicky aspect of this, but it's still a somewhat significant aspect. Now, one of the big ideas here is that not all of the chemical reactions we will deal with will be spontaneous. Typically, when we have a choice, the cells we will run will shoot for the largest spontaneous reaction. We're going to do the most spontaneous reaction because those want to go. But if you are forced with the choice and it gives you the chemical reaction as written, you have to check, is this spontaneous, is this not? Because you can have a non-spontaneous reaction occur. However, this must come when you need work. Because obviously, a battery is best served when you can recharge it. The reaction that gives you the energy, like the lead-acid battery in your car that helps start the engine, it works when it's spontaneous. But when your car runs the alternator to charge it back up so you can still use that battery again and again and again, that is a non-spontaneous, the recharge function. We use some of the work from the alternator to charge the battery. It's a non-spontaneous reaction. Now, it's possible, for example, to split sodium chloride into sodium salt and chlorine gas. Remember, that was a highly, highly spontaneous reaction that we talked about. We had negative 785 kilojoules to do that because of the voltage of like 4.069. However, if we put 4.069 volts of energy back into it, we can split it back into its original elements. Now, where is this more often going to be used? It's going to be used to put a metallic coating onto objects. So when, for example, you chrome plate an automobile or you electroplate a metal onto something like with a copper plating or something like that, if you're not doing the molten metal, you're going to use electroplating, where we put a voltage through it as we dip it into the solution. And we're going to force the metal onto the surface. Now, because this is not an instantaneous process, this takes time. There's a kinetic function here, but it's not quite a kinetic equation. We can calculate how long we need to electroplate to get a certain thickness because of one other voltage thing that we haven't learned before, and that is current. A current is like a velocity for coulombs. A current is the rate of speed of electron transfer. It's measured in the units of amperes, but an ampere is simply a coulomb per second. A coulomb per second. Now, the current along with the time used can be used to figure out how many electrons will be transferred. Then we can Avogadro using the molar mass, the moles of electrons, and Faraday's constant to figure out how much mass will be transferred. How much mass will be transferred. So you can figure out how many grams of, say, gold can you plate onto this surface if I use this current for this period of time. Everything else is constant for gold. The equation is, and I will give you this whenever we need it, mass equals current times time times the molar mass over NF. Molar mass over NF are essentially constants, and those convert our units. If you watch your units, all of it works out nicely. Oh, shoot. So how long would it take to electroplate 20 grams of chromium 3 plus? 20 grams of chromium 3 plus using a 5 amp current. And then the other question is, how much zinc 2 plus could we electroplate in 1 hour with 10 amps? The only issue is that amps are in coulombs per second. An amp is a coulomb per second. Okay. So we're going to always assume we're going to go to the solid. So mass, if I have, let's write down what we have. 20 grams, 5 coulombs a second. We want to find T. This is the unknown. We need the molar mass, we need F, and we need N. What is our N? Don't overthink this. We're going from chromium 3 plus to chromium solid. So how many electrons? 3 electrons. Well, for the molar mass, you just have to look up the periodic table. Now, unfortunately, I don't directly remember chromium right off the top of my head. That's about 52. So rearranging this to solve for T, what would you have to do? You would say 20 times 3 times 96485 divided by 52 divided by 5 would give you how long? How long? So 20, and this is not, mind you, not a whole lot, but it depends on how thick a surface. I'm not going to go into the heavy math that would be, well, now we need to calculate the surface area and the density to figure out what type of thick. No, we're not going to do that. So how long would this be? 22,265.76 seconds. Well, what is that? Don't overthink it. Well, that is 371 minutes or 6.18 hours. So at 5 amp current, to put on 20 grams of chromium, I would leave it in solution for 6 hours. 6 and like almost 2/10 of an hour. Now for zinc, how much could be electroplated in 1 hour? So zinc, we're going to zinc 2 plus. So let's look at that. We're looking, what is the mass? 10 coulombs per hour. So 10 coulombs per second. So we need to turn coulombs per, we need to turn 1 hour into minutes and 1 minute into seconds. So you'd have 3,600 seconds. The molar mass of zinc, I'm pretty sure it's like 65. We'd have to take 2 electrons, 96485. So doing that, how much could be electroplated? 96485. You would be able to electroplate 12.12 grams within an hour. Now, even though it's a little bit heavier, we're electroplating a lot less, but it's also higher current and less electrons that need to be transferred. So this is a kind of a weird equation, but all in all, hopefully you won't find this one too tricky. But It's the only equation that will use amps, and it's the only equation that will use time in this electrochemistry thing. So that's an easy way to figure out which equation we're dealing with. Now, the last little thing I'd like to talk about are the batteries among some things and corrosion. Two applications of electrochemistry in work. The whole idea, batteries have a special purpose in our terms of energy. If we look on the top right graph here is measuring energy density and gravimetric energy density. So megajoules per kilogram and megajoules per, well, I'd like to say liter. So in both these cases, you look here, diesel right here is pretty high up there, which is one of the reasons why we use it in a lot of our big rig trucks. Gasoline is not far below it. And then we get down to E85 and ethanol, again, lower and lower energy density. You get methanol and M85, lower and lower. If I try to use hydrogen in cars or methane in cars, the liquid hydrogen, these guys are pretty low energy density, but why do we consider them? Why are they being considered as fuels? Well, they're cleaner. They're renewable. You could hypothetically produce hydrogen by splitting water, remember? And even going gaseous hydrogen down here, 200 bars, it's even lower energy density. But once again, the renewability. And way down here in the very bottom are batteries, which obviously, if you look here, suck. Going to this graph, which is a blow up of there, we can see here some zinc air, some lithium ion, some of the newer batteries. And all the way down here, we have nickel metal hydride, nickel cadmium, and lead acid right here. So it's getting lower and lower and lower energy densities. But why do we even use batteries? Well, batteries, kind of the whole idea of battery is the ability to easily store energy. That the idea of you can pick up energy somewhere else and keep it around. You don't have to hold the liquid there. You can't take sunlight or wind power or water power and make gasoline out of that. You can't make methane out of that. It's not really easy. So unlike all the other technologies here, all the other types of fuel sources, we can store these. And also we can use these multiple times by recharging them. So they can be used multiple times before they're dead. And plus, when we do them, there's usually a low amount of waste byproduct. Some of them can be recycled. There's not a lot of issues that are nearly as bad as, say, diesel when we burn that. Now, lead acid batteries are like simplest, some of the oldest technologies, and still one of the most widely used. The whole idea is what happens? You have two electrodes, one of which is coated with a spongy lead oxide, the other's coated with like a lead paste. And we put this in sulfuric acid, really strong sulfuric acid, thus the lead acid part of the battery. And the reaction is essentially that the hydrogen converts both sides to lead 2+. Technically, if you look up on the chart, instead of lead 2+, they're actually converted into lead sulfate. But we can deal with them as such. Now, the conducting solution, the salt bridge, is, as I said, a concentrated solution of sulfuric acid. These guys the cells are within the same solution. Unlike the batteries we were discussing previously, they are essentially connected. The electrodes are coated, but they are not in separate jars like we have drawn in any of the other batteries. Now, there's some issues with lead acid batteries in that while discharging, you produce lead sulfate. It's convenient because this helps keep the active material where it needs to be. So when you recharge it, you can put it right back where it belongs. So there is a problem. If you leave your battery discharged for a long enough time, those lead sulfate crystals will get bigger and bigger to the point where your lead acid battery won't recharge. This is a process known as sulfation. So if you, for example, kill the battery of your car and then don't charge it back up right away, you can permanently damage your car battery by forming large sulfate crystals that won't go away. Now, the battery contains an anode and cathode. Once again, they're in the same electrolytic solution. However, they are separated by a thin porous membrane called a separator. The purpose of this is to keep these two electrodes from touching. Whenever two electrodes touch, the electrons are always going to travel on the shortest path. When they travel through solution, it's a slow process. It has to convert, and it won't naturally discharge until you connect it. However, if the two electrodes touch, they will create a completed circuit that will cause it to fully discharge. So whenever the two electrodes touch, this is called a short circuit, and battery's dead, permanently gone. The separator's job is to keep that from happening. Now, lead acid battery has all these issues that we know about, but lead is relatively cheap. We can make really big lead acid batteries for relatively easy, and they worked so far so well that we haven't bothered to try to really replace them in automobiles. I mean, yes, we could try to do like a fancy batteries like for like a Tesla, but those cost a lot of money. So we stuck with this. It's a reasonably cheap alternative. Now, there's other batteries. You may have heard of alkaline batteries or alkali batteries. What does that mean? Alkali, remember, is basic. It's an old term meaning a basic battery. So unlike the lead acid battery, these alkaline batteries use manganese and zinc in a highly basic solution. And now most of these are non-rechargeable. There's ways they've managed to find ways to recharge these to some extent, but the standard alkaline batteries aren't rechargeable because once they discharge, the active material, which is the manganese and the zinc, kind of like fall away. They disperse and they move away from the electrodes, and so you cannot get them back to where they need to be. That's the advantage of those lead sulfate crystals. They stick them, the active material, and it stays in place. Well, in this case, they move away, and so when the batteries discharge, you have a bunch of junk not at the electrodes. Now, if you look, there's some other ones, nickel cadmium and nickel metal hydride. Now, these guys, as we move up, similar reactions, much higher energy densities, very good rechargeability. However, they are kind of in limited use because of nickel and cadmium cadmium's kind of toxic. And with the nickel metal hydrides, we need lanthanides and actinides. Well, just lanthanides, but those guys are kind of rare earth metals. They're not cheap to get. So we don't use those nearly as much because it's more expensive batteries. Now, lithium ion are kind of an interesting one. Not everything is fully known about this because unlike the other batteries that transfer electrons, lithium ion batteries transfers literally a lithium ion. Would be like what? 3 protons, 2 electrons, and what, like 2 or 3 neutrons. The whole ion transfers between a cobalt oxide electrode and a graphite electrode. So instead of just a single electron, we're transferring a charged metal. So there's some weird stuff going on there. If you want more information, there should be some chapters in the book you can look at. But some really interesting stuff going on here. Now, the other thing we can talk about for this chapter is corrosion. The idea that corrosion happens everywhere. The most common thing is iron ore. Iron will naturally oxidize, and it does in the earth to form iron ore, which is how we dig it out. It's a spontaneous process. Iron 2 oxide goes to magnetite, and then magnetite goes to hematite. Now, because of this, it's going to change into various different properties such as solubility, strength, and magnetism. Iron, very magnetic. Magnetite over here, Fe3O4, relatively magnetic. Fe2O3, non-magnetic, brittle, crumbly, soluble, all the type of bad stuff. This is the rust that will flake off your automobile when it gets too old. We want to avoid that. That's when your car gets all rusty. Your car is going to, even if your engine works, it's going to be dead soon. Now, this process will not happen by itself. You need two things to occur. You need to make a battery on the surface. To do that, you need two things: oxygen, or possibly protons as an oxidizing agent, and water as the electrolyte. Just putting iron in the presence of oxygen will not make it rust. You need the water for the oxygen to dissolve into to help transfer those electrons. It won't happen otherwise. Especially acidic water will really help this along. So we need those two things. So you get wet surface with acid and water, acid and oxygen dissolved into it, it will start oxidizing. Now, how do we prevent that? I mean, obviously there's various paints that will coat the surface that will help prevent oxidation, but another way is by coating it with a more reactive metal, such as zinc. This is what happens when you galvanize steel. Essentially, what happens, you burn off all the oxides with caustic acids, we rinse it, we pickle it, we flux it, all trying to get it ready. So eventually we dip it into molten zinc. Zinc forms a nice candy coating shell on the surface of the iron. And the idea here is that zinc will oxidize. It will form zinc oxide, and eventually, in the presence of CO2, zinc carbonate. However, unlike iron oxide, zinc oxide is not porous. It is not necessarily as soluble for the water. The water, when it rusts, traditional rust will speed up other rust formation because it is very porous. Water can stick to the rust and help dissolve more oxygen and cause more rust to form. Zinc oxide and zinc carbonate form a little protective barrier that will shield the underlying iron from any oxidation. And the beauty of this is because zinc has a much higher oxidation potential, that even if iron does rust, even if the iron coating the iron underneath does rust, zinc in its unrusted state, unoxidized state, will act as a sacrificial electrode to protect the iron, to reduce the iron back down. The zinc will react before the iron and thus protect the iron for as long as possible. Now, galvanization is far from perfect. various different salt solutions and acid solutions will dissolve it. You put this in acid rain, it's not going to last super long. You put this in sulfuric, you put this in like sulfate, like high pollution areas or by the sea, it'll create different barriers that don't protect nearly as well. However, galvanization will still provide years, if not decades, more life out of certain steels and certain tools that otherwise would have rusted, corroded, and needed to be replaced. And so the whole idea of electrochemistry is all around us, whether we necessarily see it or not. It's still going around us. Now, that is this chapter. We have, like 5 minutes. We'll start looking at a little bit of the homework, but we're not going to get very far, honestly. So, not with 5 minutes. Now let's look. Okay. Okay. There's 20 problems. Let's at least look and see what type of problems we have. Problem number 1, it's all about determining oxidation state of various metals. So don't forget your oxyanions. Don't forget your oxyanions. Remember, oxygen is typically 2 minus, hydrogen is typically 1 plus. So how would I do this one? Well, remember, carbonate is 2 minus. So CO3 is 2 minus. So we can know copper is 2 plus. And if oxygen is 2 minus, and there's 3 oxygens, you can figure out what carbon must be. Don't overthink some of these guys. Halogens are typically 1 minus. Typically 1 minus. However, some of these guys are a little bit more tricky. Don't forget to scroll down. So split these into the half reactions. So let's see if I can do this. The oxidation, iron loses electrons, so Fe goes to 2, well, it goes to Fe3 plus. See if this works. Okay, and then we have the other one, which is O2 goes to 2O minus, and this needs plus 4 electrons. See, so when you guys try this problem, we know what's the issue. If this works for it. Yeah, okay. So just quick. So I split this into its component cation and anion pair, and I just figured out, oh, I don't need to balance this. I just need to I don't need to balance the electrons. I just need to figure it out. So iron, how do I know that's iron 3 plus? Because oxygen is 2 minus. 2 electrons times 3 is -6. So 2 times what is +6? Well, 2 times +3. And then I just O2. So that's pretty straightforward. Let's see. Balance the overall equation. So this one you have to do the half reactions, add them together, balance the electrons, and do all the steps. That one's pretty straightforward though. This one, assign oxidation states to species. you just have to say, what is the charge? Don't overlook some of these guys. If it's just a silver +1, it's just going to be +1. Okay, this one, yeah, we have two half reactions. You have to balance them separately and kind of put them back together. They've already kind of set it up for you. This one, you might need to add protons and water. Don't forget protons and water if the oxygens don't balance otherwise. So you'll probably need protons and water in that one. Let's see. Write the two half reactions. This one asks you to write the cathode and the anode. Remember, cathode is reduction, anode is oxidation. Setting up the parts of the electrode. Classify these descriptions. Okay. Looking at circuit, you have an interactive here to show what's going on. Let's see. We'll look at some of these more like what's the half reaction of the anode, what's the half reaction of the cathode, and then the net cell reaction. So some of these are just understanding how they're set up. This one's the first one where you actually calculate cell potential. So we don't calculate cell potential till like number 10. And number 11, same thing. We can use these numbers. So we'll look at these more on Thursday. Put these on based on degree of oxidation agent. This one we have to go to the, once again, that chart again. Hint, here's the reference. More of the chart, more of understanding that chart and seeing which one will react and which one don't react. Because we want a spontaneous E cell for a spontaneous reaction. So those will be a good show they understand. This is the first time where it's the non-standard. We'll have to do one of those. This is finding Q for the given a non-standard. Understanding the relationship with G and E. Understanding the relationship with G, E, and Q. Calculate the standard free energy change. So find delta G given E, or being able to find E. And then electroplating. So we'll look at these guys more on Thursday. We're out of time. Thank you for your patience. I will talk to you again in lab and on Thursday.